Hello everyone. So this is the lecture 2 of the course Digital Control. Here we are going to discuss the sampling and effect of the sampling rate. This is the most important for the digital control. When we are going to convert analog signal into the digital signal, our system we are going to convert into digital form. So before proceeding the current lectures, we have to discuss the previous lectures basic contents. In the previous lecture, we have to cover the classification of the control system with respect to the signals and signal representation, and give the basic description regarding the analog to digital and digital to analog converter and system stability. So what are the objectives are there? So we have to discuss the sampling and aliasing effects. So what are the sampling process and aliasing? This is the basic two objective of this current. So sampling, you know that the process of the converting a continuous time signal to the discrete time signal. So in order to computer to process the data digitally, so any continuous signal we want to control into the digital form, so you have to apply the you have to process the sampling. So we have to convert the continuous time signal into the digital time signal. Then we have to there is some demerits of the sampling. So we have to consider the few frequency labels. So there is just some problem occurs during the sampling, that is called aliasing. The phenomena where because of the too low a sampling frequency, the original signal get corrupted by the higher frequency components, sometimes known as the spectral holding. So due to the spectral holding, if we are using the sampling frequency is too low, so there is a errors we are getting during the reconstruction of the signal from the digital. Suppose we have to convert the analog signal into the digital form. Then digital signal contains the information of the analog signal. When we want to reconstruct this information of the continuous signal from the digital signal, so we are getting the some errors if sampling frequencies are too low. So that is called aliasing. So it is also sometimes is known as the spectral holding condition. So here so here we are going to see the first define the sampling process. So this is the representation. You can see we have to represent this is the relation between the continuous time domain signal and discrete signal. So this is the xt is continuous and xn is then discrete. The process of measuring the instantaneous value of the continuous time signal in a discrete form, this is called a sampling. We are going to measure the instantaneous value of the measured signal or any signal which is represented in this continuous domain. So this is the, we can say, continuous to digital form, that is the sampler. So here we are applying the analog signal and we are getting the discrete signal. So here A to D converter to turns xt into the xn. Xn is the discrete form, xt is the continuous form. So take a sample, every sampling period Ts, uniform sampling. So this Ts may be different, or sampling quantity we are taking the every sample we will be uniform, will be non-uniform. If we are considering uniform, that is we can simplify very in easy way. If we are considering the non-uniform samples with non-uniform sampling time period, then it creates the complexity and system maybe becomes unstable. So here we are consider the samples should be uniform within a uniform sampling time period. This is our objective. So here the sampling is a piece of data taken from the whole data which is continuously in time domain. Suppose we have a data, and this, suppose we are taking the 10 data is there. Suppose we are taking the 10 data out of 100 as each 10 samples. So total 10 samples we have to perform. So there is a, we have to consider when a source generates an analog signal, if that has a to be digitized having 0 or 1. So after the sampling we have to convert into the 0 1 using the quantization process. So this is the A process. We can understood how we are going to change the frequency so information may be lost. Suppose this is the continuous signal. This is the continuous signal having the frequency 100 Hz. They have given 100 Hz. So this is the cosine function. So you know that this is that when we are apply the or we are going to apply convert in the form of the discrete form, when we consider the sampling frequency is the fs equal to 2 kilohertz. Fs equal to 1 by ts. That is the sampling time. So here the sampling frequency we are considering 2 kilohertz. So we are getting the like that. So here from this signal you can see the each information of the continuous signals are preserved. So there is a, if you want to convert or we want to get the continuous signal from the this digital signal, we can get the very easily using the digital to analog converter. And this is the signal we have to consider here the based on the 500. Here we have considered the 500 Hz frequency. So based on the 500 you can see these are the sample times. So here we can see between these points we are getting the approximate value. So when we are trying to retrieve the original signal, so it creates some problem. So it may be we can get, but suppose we are considered the 500, here we are considered the suppose 150 Hz, we are getting them furthermore. So this is the way we can change the sampling frequency and we can get the or we can preserve the information of the continuous signals. So here in the sampling process we have to consider the take care of the two values. One is the sampling fs, second is the sample value. Sample value we are consider the this is the should be uniform for each, and frequency when we are making this is the uniform, then fs will be playing main role. So you know that here we are sample 2 kilohertz, we are getting such type of information. So a digital signal, if we are using 500, we are getting this one. So which one is the more accurate? This is the confusing part. Then the researcher have given the some terminology that is called a sampling theorem. So using this sampling theorem, we can say that the bridge between a continuous time and discrete time. So they give the relation between. So this sampling theorem tell us how often we must sample. So what are the sampling frequency should be there, it gives the information to in order to extract the information without any loss. So we can define the sampling theorem, that is also it is called sometimes Shannon sampling theorems or Nyquist theorems. So sampling theorem is a continuous time signal xt with frequencies no higher than f max. Suppose a signal has the lot of the frequency represented in the continuous domain, having the frequency suppose 10 Hz and 50 Hz and this is the combination of 100 Hz. So we are consider the maximum frequency, this is the 100 Hz. So a continuous time signal xt with frequencies no higher than the f max in Hertz can be reconstructed exactly from its sample. This is the sample where ts is the sampling p time, n is the integer. If the samples are taken as at a rate fs equal to 1 by ts, this is the sampling frequency and ts is the time period, sampling time. that is greater than the twice of the frequency, twice of the f max. Means sampling frequency fs should be greater than equal to f twice of f max. Means if signal have the several frequency, you have to calculate first what is the f max, maximum frequency, then make the twice of this maximum frequency. So sampling frequency should be greater than equal to of this twice of maximum frequency. So this sampling theorem provides the answer how often we must sample of a signal in order not to lose any information. So it is stated that if original signal has the maximum frequency component at f max, then we must sample the signal twice of the f max or higher order not to lose any information. If we are going to sample this signal very low frequency, so it creates the problem. So in next slide, here we are considering, here you can see, so this is the a time domain signal xt represented, and this is the frequency domain representation. This is the time domain, this is the frequency domain. So you know that this is the frequency domain representation. When we are multiply this time domain with the samples, means this is the train of the impulses, we are getting the discrete signal. This is the train of pulses, we are getting the discrete signal. Here we are simply using the multiplication, a dot. And in frequency domain, here we are using the convolution. So multiplying two signals in time domain is equivalent to the convolution their spectrum in the frequency domain. Here we are simply multiplication in the time domain, but in the frequency domain we have to take the convolution. This is also train of the impulse signal, and this is the, when we are multiplying we are getting this is the signal. So here we have to extract the actual signal, means this is the discrete form, so actual signal, so we have to design a low pass filter that is nothing but as a zero hold order circuit. So this is the basic way we have to conversion of the product in time domain into the frequency domain. It is equivalent to the convolution of the signal. So here the sampling theorem tells that, you can see this is the A to reconstruct original signal xt. Here we have to design the low pass filter. So in this red line you can see this is the low pass, ideal low pass characteristics. This is the our original signals. We want to extract this signal from the distal signals. So we have to take a proper low pass filter. So cutoff frequency of this low pass filter should be matched with this original signal. This is only possible if the shaded part do not overlap. If this shaded part is overlap with this shaded part, then we can face very difficult to extract the original signal. So this means the sampling frequency should be greater than twice of the maximum frequency. So this is the called as the sampling process. So that's why we are measure the we are calculate give the more impact the sampling frequency. Here it shows that the filtering process is a low pass filter. Only it will retain frequency components or remove the higher frequency components, that is called a restriction process. So here we are going to design the low pass filter, means we can retrieve the information from this one. Here first case we are consider the, suppose the frequency are the too slow. So this is the if function we are representing in the time domain, and when we are converting into frequency domain, this is the we are getting. So suppose that we are giving the sampling frequency 10 Hz, but the signal frequency is the 5 Hz. This is the 5 Hz frequency. Here the 550. So frequency is the 5 Hz. So we are getting this much, and we are giving the sampling frequency fs equal to 10 Hz. So when we are multiplying the train of impulses means samplers, so we are getting this type of discrete signal. And when we are like taking the convolution, so we are getting this signal in frequency domain. So you can see they are here overlapping. They are exact matching. Means we are taking the Fs equal to twice of F max. When we are defining the filter, low pass filter means extract the information, you know that we can see the exact. If they uh, any this is the representation, you can see the this is the condition. At this point we have to cover. So this is the way we are representing. So you can see here we are consider the Fs is equal to twice of F max. So second we are considering the signal. Suppose here the frequency sampling frequency we are consider the something different as the previous. So this is the discrete signal, and here we are sampling at the higher than the Nyquist 20 hertz we are considering. So 20 hertz we can consider this is the gap we are finding. This gap we are finding. So in previous case we can see that we are considering the ideal filter, but in practically it is not reliable. If Fs is equal to twice of F max, we can feel the some information we are going to lose during the conversion. But when we are considering the sampling frequency much larger than the twice of the F max, then we are getting this gap. So this is the ideal representation of the low pass filter. So we can easily extract the information. So here one example is given, effect of the aliasing. Here we are giving the Nyquist rate, means a sampling frequency 5 Hz. Exact. This is also 5 Hz. So you can see there is overlapping. This is the overlapping. This is the overlapping. This is the overlapping. When we are going to extract the information, either using the ideal condition. So you can see this is the ideal condition. So this much information we are going to lose. So there is overlapping. So this effect is known as the aliasing, that is the folding of the spectrum. So at this region we can see the both spectrum, this and this, both are the lie. They are folded each other. So extraction of the information during this condition is very difficult. So such phenomena is called the aliasing effect. So now move to the further. So there is a what is the spectral folding effect of the aliasing? Suppose here we are consider the two signal. One is the 1 Hz, second is the 6 Hz, and we are sampling these two signal using the 5 Hz signal. So here you can see this is the 1 Hz and this is the 6 Hz. So you can see here so 1 Hz and 6 Hz sine waves are indistinguishable after samples. So these are the samples. In general, if a sinusoidal of a frequency 1 Hz is sampled at the Fs samples per second, then sample version would appear as a sample of the continuous time sinusoidal Fa in order of the 0 to Fs by 2. So you know that if signal is sampled with the 1 Hz, so you know that we are getting this is the sampling. This is the sample instant. So you can see that the 6 Hz frequency is folded over the 1 Hz frequency. In other words, 6 Hz sinusoid is folded to 1 Hz after being sampled with the 5 Hz frequency. So this is the spectral folding effect of the aliasing. So to avoid the aliasing effect, we have to use the anti-aliasing filters. So to avoid the corruption of the signal after sampling, one must ensure that the signal being sampled at Fs is band limited to a frequency F, that is B. So here you know that this is the B. So B should be at this is the plus minus B. So B should be less than Fs by 2 sampling frequency. So consider a signal, this is the having frequency B. So after sampling we are getting this is that. So you can see this is the part. So this is the overlapping region here, 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 everywhere. If you want to extract using the ideal pass filter, you know that this is the loss. When we are projecting after the reconstruction, you can see we can extract this form, and we are getting the like that. Here at this part we are getting there is some loss. We cannot extract the exact information of the signal, and here we are getting the some folded in the trail. So these two regions are going can affect in the terms of the information loss. So we have to minimize the using the anti-aliasing filter. So here we have to apply a signal to low pass filter, that is the xt, that is the sampler, then apply to the sampler with the multiply the train of pulses, this is the low pass filter. So we have to xt means apply to the low pass filter. What are the other components, major low pass frequencies are can pass, and higher pass frequencies can block. Then apply the sampler multiplied with the train of pulses, convert into the discrete. So this is the way using the anti-aliasing filter. This is the anti-aliasing filters. So anti-aliasing filter means this folded region they are neglecting. Only that this is the part we are going to minimize using the sampling process. If making the frequency is larger, then we can minimize these terms. So this is the part. So we can minimize the corruption of the signal. So in ideal low pass filter, this is the characteristics of the ideal low pass filter. So that is represented in the form of the sinc function. In the frequency domain, this is the representation. When we are obtaining or multiplying with the this filters using the samples train of the impulse train, so you can represent in the form of this signal. We are not going to in detail, so this is the information purpose. So how anti-aliasing, aliasing effect, sampling, so we can consider. This is the ideal signal reconstruction. So practical signal construction, you know that this is the ideal case, we are considered ideal, and this is the practical. But here you can say this is the ideal filter characteristics, low pass filter characteristics. But practically we cannot achieve. So we are achieving like that. There is some inclination. So there is some way like that we are getting the sum like. So we are getting the sum inclination. So this point we have to consider. So in ideal case, this is the like that. But in practically it is not possible. So we have to normally sample the signal much means higher frequency than Nyquist rate, means twice of f max. This is the overall the conclusion of this lecture. So here the ideal signal construction you can see. So this low pass filter we can see the here again we are converting the digital signal into the analog signal using the interpolator to that perform the job of the signal restriction. It is sometimes called a zero order hold circuit. This is represented by ZOH. So this is the represented by convolution. So here this is the discrete signal. We have to apply this one. Then we have to convert in the form of the several steps you can see. So again the effect of the zero order hold of a DA converter is a non-ideal low pass filter. So this is the again we are converting the analog to digital form. So there is some problem. Again here when converting the digital to analog signal, so zero order hold circuit, this is also nothing but is a low pass filter. So this is the low pass filter characteristics. This is the ideal case, but practically we are not receiving this ideal case. There is some inclination. So we have to consider during the sampling. So each sample have give some information. Suppose this is the perfect ideal. Here ideal we are using for this sample we are sampling for this. What if this is the and like that we are getting. So this is the way. So we can conclude the overall sampling this lecture. So we already discussed the sampling theorem, sampling rate, aliasing effect, and aliasing filter design. So we can conclude that the sampling frequency Fs should be greater than twice of F max. Or we can say that if you are this is the a major relation when we are going to convert analog signal into the digital signal. So this is the a major part of the signal analog to digital conversion.